The setup we are using today uses this signal spectrum analyzer connected to the output of the generator. Today we will be using the older style analog signal generator because its controls are much easier to use and relate to with the spectrum. The output of the signal generator goes to the spectrum analyzer and also to the scope, channel 1. Also, we will use the modulation output, the modulation section, and take the signal out and drive the oscilloscope. This will make it much easier to trigger the oscilloscope and get a good view. As we see on the oscilloscope, the AM signal. The modulation controls are on this section. The modulation value M sub A is controlled here, which is the level of the modulation E sub M term. The frequency of modulation is controlled by this signal, and the modulation function, AM, FM, or sweep, and the modulation type, sinusoidal, triangle, square wave, are controlled here. We will use AM and we will use sinusoidal modulation for this laboratory. The control of the modulation performs the function of controlling the AM modulation depth. Notice how the valleys and peaks are controlled by the modulation control. Changing this control changes the amplitude modulation, changes the amplitude. The carrier is unchanged. There is no modulation, there is modulation. The carrier is halfway in between the valley and the peak, and it is unchanged. The carrier is controlled by the other side of this generator. The carrier frequency, currently set on 100 kilohertz, and the carrier amplitude, E sub C term, F sub C, or omega sub M term, C term. Let's see what happens when we change the carrier. When we change the carrier, we change the whole waveform up and down. So that is the E sub C control. The F sub C, or carrier frequency control, is actually not visible to a large degree on the scope because we're not looking at high frequencies, we're looking at lower frequencies. So if I change from up to even 600 kilohertz, the signal, modulation signal, is unchanged. And this is a good thing because we don't want our information, which is in the modulation, to change with the carrier frequency. Every radio station that plays the same song should have the same modulation waveform. And this shows that it does. Change from 600 to 300 kilohertz, and the waveform looks the same. Now, on the spectrum analyzer, we will go back to our original condition and we will look on the spectrum analyzer. On the spectrum analyzer, the carrier is in the center. We are peak searched on the carrier, and we see the two sidebands of the modulation terms. In this case, 100 kilohertz is our carrier, and about 1 square, a little more than 1 square, or about 12 kilohertz is our modulation frequency. If I change the modulation E sub C term up and down, down goes the carrier is smaller. Increasing the carrier increases all of the signals, E sub C and E sub the sideband terms. If I change the frequency of the carrier by changing this dial, change the frequency of the carrier, you will see all three terms move. Why? Because all three terms, carrier and upper and lower sideband, are controlled or affected by the F sub C term. We will track back on the signal and it will lock in. If I change the modulation control is over here. If I reduce the modulation, remember I come back to this kind of signal, reduce the modulation to 0, no amplitude modulation, and of course that means all we have is the carrier. As I increase the modulation, I see the modulation terms appear. If I change the modulation frequency, which is controlled here, I'll lower it down. I change the envelope or the outside part of the waveform. Higher frequency of modulation, lower frequency of modulation. Higher frequency, we will see the difference on the spectrum analyzer. Higher frequency of modulation, lower frequency of modulation. If I make it low enough, the signals will disappear into the carrier term. So be careful about your span. If I span down, I will see the signals inside. Got a little too low there. Two sideband terms. Increasing the level of the sidebands increases their value in the time scale. I'm on the linear mode of the spectrum analyzer, by the way. Linear mode is much easier to look at. If we switch to logarithmic mode, we see lots of signals. It gets a little confusing, so stay on the linear mode. Now, you will notice that as I increase the modulation input, I can get to a maximum value, and then we go over modulated, greater than 100%. This is not what we want. The maximum modulation is 100%, where the valley goes to 0. If we look at that point, uniquely, the valley occurs. The modulation terms will be half the size of the carrier. Half the size of the carrier, because, remember, the modulation terms are split in half. E sub m over 2, E sub m over 2, E sub c. If we look here, the carrier's in the middle, E sub c m over 2, E sub m over 2. So the difference between the peak and the valley is E sub m. That's 100% modulation. If we overmodulate, we start to create signals in this area, which is not AM modulation, not standard AM. So 0 modulation, E sub m term is 0, 100% modulation. That's in the time domain. In the frequency domain, E sub m is 0, E sub m is maximum. That's the laboratory for tonight, to understand the spectrum analyzer and the scope and AM modulation terms.